Howdy. This video is on the basics of electrochemical reactions. There are many electrochemical reactions, including formation of rust, combustion. Many reactions in biological systems are electrochemical. Obviously, reactions in batteries are electrochemical. And so many reactions are electrochemical, not just the reactions in batteries. Now, when you have elements oxidation that changes, going from reactants to products, that's going to be electrochemical reactions. Also kind of cool, for electrochemical reactions, we can actually rank a compound's ability to be either oxidized or be reduced. And so similar in terms of acid base chemistry, you can actually rate compounds based on how strong acid or how strong a base they are. In electrochemical reactions, you can also rank compounds on how good of oxidizing agent they are or how good of reducing agent they are. What you should be able to do after watching today's video is assign oxidation numbers to elements in compounds, identify what is being reduced and oxidized in a reaction, as well as the reducing agent and oxidizing agent, identify electrochemical reactions, and determine how many electrons are transferred in a reaction. The basis for understanding electrochemical reactions is the oxidation state. So again, remember that it's only an electrochemical reaction if the oxidation state of two elements change going from reactants to products. And so in Bronsted acid-base chemistry, it was about transfer of hydrogen ions. And so we have HF going to water, forming F- plus hydronium ion. And so in this reaction, HF is losing hydrogen. We call that the acid. Water is gaining the hydrogen. We call that base. In electrochemistry or electrochemical reactions, we have a transfer of electrons. And so in the reaction, copper plus silver ions going to copper ions plus silver metal. Notice that the silver ions are going from plus and then you're forming silver metal. And so each silver ion is gaining an electron. Each copper metal atom is losing 2 electrons. And so we actually refer to the copper going to copper 2 plus as oxidation, is losing electrons. We refer to the silver plus ions going to silver metal as reduction. The silver is actually gaining electrons. Now I can view these two as an oxidation and reduction half reactions. The 2 electrons in the oxidation step or half reaction is exactly the same as the 2 electrons in reduction. And so electrochemical reaction, you actually have a transfer of electrons from one species to another species. And so electrotransfer reactions are redox reactions, reduction-oxidation, which we refer to as redox reactions. They're just electrochemical reactions. And so redox reactions, electrochemical reactions, you can use those two terms interchangeably. Redox reactions can result in generation of electric current, can be caused by imposing electric current, or neither. Again, remember that many reactions are electrochemical, formation of rust, combustion, just electrochemical reactions because you have a change in oxidation state of 2 elements going from reactants to products. Now, oxidation is defined as loss of electrons by a species, and hence if you lose electrons, you're increasing the oxidation number. Remember, electrons are negatively charged. Reduction, you have gaining electrons by a species, and so if you gain electrons, you're reducing the oxidation number because, again, electrons are negatively charged. Now, oxidizing agents, what causes the oxidation? And so the oxidizing agent is always what is reduced. Reducing agent is what's causing the reduction, and so reducing agents are always oxidized. Now, one way of remembering this is Leo goes Gur, lose electrons oxidation, gain electrons is reduction. And so we can characterize atoms and molecule by their oxidation state or oxidation number. I'll use oxidation state and oxidation number interchangeably. Now we use oxidation state and oxidation number to track the electrons. And again, oxidation number is the charge an atom would have if the bonds were purely ionic. We can also use formal charge to characterize atoms in a reaction. Formal charge is the charge an atom would have if the bonds were purely covalent, if the bonding electrons were completely equally shared. Now, formal charge is used to identify or determine the structures that are most stable. Oxidation state used to monitor the transfer of electrons. And so again, please remember oxidation number, oxidation state. I'll use those two terms interchangeably. It's the charge an atom would have if the bonds are purely ionic, meaning that the bonding electrons go to the most electronegative.
The common oxidation numbers of the elements exhibit periodic trends. For example, the common oxidation numbers of the alkali metals are all 1, while for the alkaline earth elements of group 2, they are 2. These values correspond to the numbers of valence shell electrons in the atoms of these elements. As we move from left to right across a given row, the maximum oxidation number observed increases regularly to +7 at manganese. From lithium to boron, the commonly observed oxidation number increases from 1 to 3. Carbon can have more than one oxidation number. For example, -4 in a covalent compound such as methane, CH4, +2 in a compound such as carbon monoxide, or +4 in a compound such as carbon dioxide. Nitrogen similarly has several different oxidation numbers in the various compounds in which we find it, ranging from -3 in a compound such as ammonia, NH3, to +5 in a compound such as nitric acid, HNO3. The more electronegative elements, oxygen and fluorine, show only negative oxidation numbers in their commonly observed compounds. The elements of the third row of the table show a similar variation in oxidation numbers. Notice that the most positive oxidation number observed for each element increases steadily in moving from sodium to chlorine. Notice that chlorine and sulfur have positive oxidation numbers. These occur in oxides and fluorides of these elements, because chlorine and sulfur are less electronegative than oxygen and fluorine. In the fourth row of the table, we encounter the first transition metals series. Notice that the maximum oxidation number increases regularly to manganese. As we move beyond manganese, the most common oxidation states for the transition metals are +2 and +3. For the nonmetals in this row, the observed oxidation states are very much like those of the corresponding
second row. Now it's kind of interesting. Notice that in general, the maximum oxidation number, the most positive, corresponds to the number of electrons that the element will have to lose to get the noble gas configuration. This is true except for the transition metals. The transition metals are a little bit different because they have those d electrons. And so most elements exhibit a range of oxidation states. Which oxidation state they are depends on what they're bound to. And so, again, if you look at nitrogen, it can actually go from a +5 to a -3. And it depends on if it's bound to something that's more electronegative or less electronegative. If it's bound to something more electronegative, then the nitrogen will have a positive oxidation state. If it's bound to something less electronegative, then it will get the bonding electrons and it will have a negative oxidation state. Now, so for many compounds, they'll have a wide range of oxidation states, like carbon, nitrogen, phosphorus, sulfur, silicon, etc. In a compound, alkaline metals will have a +1 oxidation state. Alkaline earth metals will have a +2. So that's in a compound. By themselves, they're just going to be metals, and their oxidation state will be 0. But in a compound, alkaline metals will be +1. Alkaline earth will be +2. In a compound, fluorine will be a -1, except for F2, where it will be 0. In a compound, oxygen will typically have a -2 oxidation state, except if it's bound to fluorine, and they will have a positive oxidation state. But typically, oxygen will be in a -2 in a compound. Hydrogen will typically be a +1 oxidation state in a compound. Now again, F2, both fluorines will be 0. O2, both oxygens will be 0. H2, both hydrogens will be 0. And so you can be fairly confident on knowing the oxidation states of the alkaline metals, alkaline earths, metals, fluorine, oxygen, and hydrogen. And again, please remember when elements are by themselves and have no charge, so lithium metal, magnesium metal, oxygen gas, fluorine gas, hydrogen gas, they have an oxidation state of 0. Now, to me, the easiest way to determine oxidation states, well, there's two different ways. One way is using two rules. That's fast. It works about 95% of the time. The second way is doing Lewis electron dot structure, or electron dot diagram. I always start with the two rules, and then if that doesn't work, then I go Lewis diagram. But the two rules are much faster, and again, it works 95% of the time. And so the first rule is you can be fairly confident in the oxidation states of a few elements based on electronegativities. Fluorine's the most electronegative element on the periodic table, and so in a compound it will be -1. Oxygen is the second most electronegative element on the periodic table, and so typically it's a -2. Alkaline metals, alkaline earths, alkaline metals +1, alkaline earths +2, and hydrogen typically in a compound will be a +1. And so there's some elements that you can be fairly confident on what their oxidation states are. Now, for the ones that you're not sure, what you do is you take the sum of the oxidation states of the elements of a compound, and it has to equal the net charge of the compound. Okay, so basically what you do is you look at your compound, you figure out what elements you're confident with, for example, fluorine, oxygen, hydrogen, alkyl metals, alkaline earths, and then you add up all the oxidation states and you try to solve for the ones that you're not confident with. And so just using these two rules, you can get oxidation states 95% of the time. If it doesn't work out, you'll notice, we'll go through an example, and then you can use the Lewis diagram method. And so going for carbon dioxide using the two rules, oxygen should be a -2. And so the sum of oxidation states equals the net charge. And so 2 times oxidation state of oxygen plus oxidation state of carbon has to equal the net charge. CO2 is neutral, and so the net charge is 0. Oxygen is typically -2, and so 2 times -2 gives you a -4, plus oxidation state of carbon equals 0, and so the oxidation state of carbon has to be a +4 in CO2. Now we can also do this using Lewis diagram. For Lewis diagram method, we draw the Lewis diagram, and then we draw it with the bonding electrons going to the most electronegative. And so you should remember in your periodic table, as you go up and to the right, elements get more electronegative. Oxygen is more electronegative than carbon, and so oxygen gets those bonding electrons. Now what we do is oxidation number is going to be the number of valence electrons of the free atom minus number of valence electrons of the bound atom, with the bonding electrons going to the most electronegative. And so for oxygen, it's in the 6th column of the periodic table, and so an atom of oxygen has 6 valence electrons. Now notice on the right, we have 8 electrons around the oxygen, and so 6 minus 8 gives us oxidation state of -2 for the oxygen. Carbon is in the 4th column of the periodic table, so it has 4 valence electrons for the free atom. Now if we look at how we drew it on the right, we see 0 valence electrons. 4 minus 0 gives you a +4. And so by this way, we still get carbon as a +4 oxidation state and oxygen as a -2, the same that we got previously. And again, the sum of the oxidation states equals the net charge. And so 4 minus 2 gives us 0. And so for the two methods, using the two rules or using the Lewis diagram, we got exactly the same value. Now again, notice that oxygen is more electronegative than carbon, and so it gets the bonding electrons if we're assuming the bonds are purely ionic. And so oxygen is going to have a negative oxidation state and carbon has a positive oxidation state. If we look at another example, here we have methane. If we do the two rules, carbon can have a range, we're not sure. Hydrogen is +1, some oxidation states equals net charge. And so 4 times oxidation state of hydrogen plus oxidation state of carbon has to equal the net charge. Methane has no net charge, so the net charge is 0. Hydrogen is typically +1, so 4 times 1 gives us 4, plus oxidation state of carbon equals 0. And so we -4 from both sides, and oxidation state of carbon has to equal -4. And so the two rules are fairly easy. Again, fluorine is typically -1, oxygen -2, hydrogen +1, alkyl metals +1, alkaline earths +2. Now we can use the Lewis diagrams. Again, for Lewis diagram method, we draw the Lewis diagram as if the bonds are purely ionic. And so carbon's more electronegative than hydrogen, so the carbon gets the bonding electrons. And now we do valence electrons free atom, which is just basically the column number, minus the valence electrons in the bound atom with the bonding electrons most electronegative. And so for the carbon, it's in the 4th column, and so it has 4, the free atom has 4 valence electrons. Now how we drew it on the right, assuming bonds are ionic, we have 8, so 4 minus 8 gives us -4. And so that tells us carbon should be a -4, same number we got for the two rules. For the hydrogens in the 1st column, so the free atom of hydrogen has 1. And notice that because it's less electronegative than carbon, it has 0 when you assume the bonds are ionic, and so 1 minus 0 gives us a +1. Again, we get the same exact oxidation numbers if we use the two rules or if we use the Lewis diagrams. And again, the sum of oxidation states equals the net charge, so it's 0. And again, notice that carbon is more electronegative, and so in this case, it's going to have the negative oxidation state. Hydrogen is less electronegative, so it has the positive oxidation state. And so we looked at the CO2, and the CO2 carbon's oxidation state turned out to be positive because it's bound to something more electronegative than it, so the bonding electrons go to the oxygen. In the methane, carbon has a negative oxidation state because it was bound to something less electronegative, so it gets the bonding electrons. And so the oxidation state of an element depends on what it is bound to. If we look at another example, here we have the ammonium ion. And so again, the sum of the oxidation states equals the net charge. In this case, the net charge is a +1. And so 4 times oxidation state of the hydrogen plus oxidation state of nitrogen equals the net charge. And so 4 times 1 plus oxidation state of nitrogen equals a +1. And so we subtract 4 from both sides, and we get the oxidation state of nitrogen in the ammonium ion has to be a -3. Now, if we do using the Lewis diagram, again, we draw the bonding electrons to the most electronegative, and so nitrogen's more electronegative than hydrogen. And then we do number of valence electrons, free atoms, minus number of valence electrons in the bound atom, assuming bonding electrons are most electronegative. And so nitrogen's the 5th column of the periodic table, and so free atom of nitrogen has 5 valence electrons. Now, the way we drew it on the right, it's surrounded by 8, so 5 minus 8 gives us a -3 oxidation state for nitrogen, same as what we got before. For hydrogen, 1 minus 0 gives us a +1. And so again, we get the same oxidation states if we're using the 2 rules or the Lewis diagram. The 2 rules, a little bit faster though. And again, the sum of oxidation states equals the net charge, and so we get that net charge of +1. Ammonium ion has a +1 charge. And again, nitrogen has a larger electronegativity, so it gets the bonding electrons, and so it ends up with the negative oxidation state, and hydrogen has the positive oxidation state. And so if we look at a range of these things, silver by itself should have an oxidation state of 0. Copper +2 is going to have the oxidation state of the charge. Remember, the sum of the oxidation states equals the net charge. You have a copper +2 ion, and so the net charge is +2, and so that means the oxidation state of the copper ion has to be the same as the charge of the ion, which would be a +2. For ammonia, we would do 3 plus oxidation state of nitrogen equals 0, so the nitrogen has to be a -3. ClO minus, and so oxidation of chlorine -2 equals -1, and so chlorine in this case would be a +1. For the phosphoric acid, it's a little bit more complicated. You have 3 pluses, 3 plus 1 for the hydrogen, 4 minus 2 for the oxygen, -8, so that gives you ends up with a +5. For the manganese, you have going to be a +7, Cr2O7, and so in all of these so far we can use the sum of the oxidation states equals net charge, and oxygen is going to be a -2, hydrogen a +1, etc. Now, if we try the 2 rules for the C3H8, which is propane, it gets a little confusing because oxidation state cannot be a fraction. And so we get a -2 or -3. And so I mentioned that the 2 rules work 95% of the time. So it works on the top 7 of these. It does not work on the propane because, again, oxidation state cannot be a fraction. And so we have to use the Lewis diagram. And so if we draw the propane, and again, carbon's more electronegative than the hydrogen, just a little bit. And so we get that. And now again, it's number of electrons free atom minus number of electrons bound atom. And so for carbon, it's in the 4th column, so it has 4 valence electrons. And so if you look on the outer carbon, it's surrounded by 7 electrons, so 4 minus 7 gives us a -3. And if you look at the center carbon, it's surrounded by 6, and so 4 minus 6 gives us a -2. And so oxidation state of the carbon in the center is actually different than oxidation state of the carbon, the outer 2 carbons. I should also mention that oxidation states are not affected by the coefficient in front. So if you're looking at these in terms of reaction and they have a coefficient in front, that does not affect the oxidation state. And again, if an element is bound to something that is more electronegative, the element's oxidation state will be positive. If it's bound to something that is less electronegative, then it gets the bonding electrons, and so the oxidation state will be negative.
A yellow solution of vanadium in its +5 oxidation state is poured into a large flask containing a zinc amalgam. The zinc serves as a reducing agent for the vanadium species. In the process, the zinc is oxidized to zinc 2 ion. When the flask is swirled, the vanadium changes to a light blue, indicating a +4 oxidation state. Swirling increases the contact between the zinc amalgam and the aqueous vanadium solution. Further reduction produces a deep green vanadium +3 solution. With even more swirling in the amalgam, the vanadium is ultimately transformed to purple vanadium plus 2.
So it's kind of a cool reaction. What's happening is the zinc is transferring electrons to the vanadium, and so you're starting with the plus 5, and then it gains electron, forms a plus 4. The zinc transfers another electron that gives you a plus 3, and then another electron actually gives you a plus 2. And so all the electrochemical reactions, all redox reactions, you have a transfer of electrons from one species to another species. So oxidation is a loss of electrons by a species, increase oxidation state. Reduction is a gain of electrons by a species. Decrease in oxidation state, oxidizing agents, what's caused oxidation. Reducing agent is what causes reduction. And so please remember, it's all about oxidation states. And so to determine if it's a redox reaction, you have to determine what's the oxidation state of all the elements. Redox is the same as electrochemical reaction. I hope that helps.